Hi there, my name is Dylan, and welcome to this fourth lesson in the series Introduction to Functions, which is called Precisely. Now, when you are sick and you need to take medicine, have you ever noticed how specific the dosage is? Do you actually read the pamphlet inside the medicine box? Well, here are some extracts from actual pamphlets. This medication is for children. The dosage increases for older children. Children under the age of 12 may not drink this medication. A maximum of 2 tablets may be taken per day. And this dosage changes for different ages and is dependent on the patient's mass. This is the dosage for a specific antiretroviral drug. Have you heard of antiretroviral drugs? These are drugs that can help extend the life of people living with HIV. Now, you saw that the dosage for these drugs is very precise, so it's very important that the amount is measured accurately. And to help people do this, some manufacturers supply a pipette so that you can measure the dosage accurately. Because sometimes in life it's not good enough to round up to a whole number. Guessing or estimating can be life-threatening in cases. Now, in this lesson, we're going to be looking at some mathematical tools that help us to find the most accurate or precise value. By the end of this lesson, you should be able to apply function notation and solve for the values of the variables. In a previous lesson, we rounded up the mass of cans to the nearest kilogram, as this approximation was good enough. But when it comes to medication, we need to be far more accurate. Think back to the dosage requirements for the antiretroviral drugs. For infants younger than 30 days old, it requires 2.3 milligrams per kilogram of body mass. Now, what if the medication suppliers provided a graph on the pamphlet? It might look something like this. Now, for a baby whose mass is 3,6 kilograms, we can read off the dosage at this point here. Or can we? Would you be confident that the reading was spot on? Well, I wouldn't be, especially if the baby's life could be harmed. So what do we do now? Can you think of any other mathematical tools we could use? Well, we could use a flow diagram, I suppose, but they take a long time to draw up, and we've got no place to write down our input and output value pairs. So in mathematics, we often use function notation. But what is a function? Well, let's investigate. Appliances and equipment all have a specific function. What do you think the function of this kitchen scale is? Most people would say that the function of this scale is to weigh ingredients like sugar or flour, but it can also be used to measure the mass of this pen or even this bottle. So the kitchen scale has one function, and that is to measure mass. Now, mathematical functions work in a very similar way to equipment or machinery. They also always have one purpose, and they act again and again the same way, irrespective of the input values. We have used a number of tools to investigate input and output values for functions. For now, we are going to focus on function rules or formulae. Let's make sure, though, that we all understand what we mean by a function. A function describes the relationship between variables, also called the input and output values. For each one input value in a function, there is only one output value. All the examples we've used so far in this block have been examples of functions. Think about the formula y equals 6,5x. Now, if my input value x is equal to 2, then y will equal 6,5 multiplied by 2, so therefore y will equal 13. One input value gives me one output value. Now consider this formula. Y is equal to 0,4x minus 20. If I let my input value x equal 1, then y will equal 0,4 multiplied by 1 minus 20 And so therefore y will equal minus 19, 6. Again, one input value gives me one and only one output value. So both of these formulae represent functions. Formulae help us to find accurate, exact answers. Remember, we weren't quite happy reading off the baby's dosage for the antiretroviral drugs from the graph. So let's use a formula to find the exact dosage. The first step is to read the information given and to identify the variables. Remember that variables are the values that change. Can you identify what changes in this situation? Well, for one, the dosage will change because it depends on the body mass. And obviously, as a baby grows, its body mass will change. Hence, the mass is also a variable. But we need to identify which is the dependent and independent variables. And here's a clue. The dosage is based per kilogram of the body mass. So we're clearly working with a function. Thus we can see that the dosage depends on the body mass. And as we said previously, we normally assign y to the dependent variable and x to the independent variable. Now x is the body mass and its units are in kilograms, while y is the dosage and its units are milligrams. Now, by now we should know that the formula for the dosage, y, is equal to 1,3 multiplied by x, that's 1,3 milligrams per kilogram of body mass, plus 1, because we need to add 1 milligram on. The next step is to give this function or relationship a name, and we generally use symbols or letters to label our functions. Now, because my name is Dylan, I'm going to call this function d. Now, there are a number of ways of representing a function. This is one way we can write it. D is equal to the set of all ordered pairs x and y such that y is equal to 1,3x plus 1. The language and symbols that we use are very important. We use curly brackets or braces for the set, and we use round brackets for the ordered pair. Here we say that the function d maps x, our input values, onto 1,3x plus 1. Another way of saying this would be to say that d maps x onto d of x. And this portion here is an abbreviated way of saying the result of function d on the input value of x. To become familiar with the terminology, read this out aloud. Function notation allows us to write mathematical equations clearly and simply. Now that we've sorted this notation out, we can get back to our example. Remember, we need to determine the dosage for an infant whose mass is equal to 3,6 kilograms. And we need to find the output or y value. Remember, we've got various different notations we can use. Firstly, for d, y is equal to 1,3x plus 1. And therefore, when x is equal to 3,6, y is equal to 1,3 multiplied by 3,6 plus 1. An alternative notation we could use is the mapping notation. D will map 3,6 onto 1,3 multiplied by 3,6 plus 1. Or lastly, d of 3,6 is equal to 1,3 multiplied by 3,6 plus 1. Does this remind you of what we did with a flow diagram when we were trying to calculate profit? Each output value depends on the value of the input. This is the same as what we're doing here. Now, firstly, we need to estimate what 1,3 times 3,6 is equal to. Well, I know that 1,3 multiplied by 4 is equal to 5,2. So whatever this answer is, I know that it must be less than 5,2. And if I calculate this using a calculator, I get an exact answer of 4,68. Now, I know that y is equal to 1,3 multiplied by 3,6 plus 1, which is equal to 4,68 plus 1. In other words, y is equal to 5,68. Now I'm going to fill this answer in using the various forms of notation we have. Firstly, for D, when x is equal to 3,6, y is equal to 5,68. Or we can write D maps 3,6 onto 5,68. Or lastly, D of 3,6 is equal to 5,68. Now, all three of these notations tell me exactly the same thing. They tell me that I have the following ordered pair: 3,6, 5,68. But what these different function notations allow me to do is to write mathematical equations clearly and logically. In this case, the use of a formula allowed us to calculate an accurate value for the dosage. We would not have been able to find such an accurate value using our graph. So we can confidently say that for an infant mass 3,6 kilograms, we need to give them 5,68 milligrams of this particular medication. Are you ready for your task? Please write it down. This is the dosage for any patient older than 1 month. For one medication, the dosage is 2,1 milligrams plus 4,6 milligrams per kilogram of body mass. Firstly, define the variables and use function notation to describe this. Determine the dosage if the patient's mass is 6,9 kilograms. And lastly, determine the patient's mass if the dosage is 48,1 milligrams. I hope that you enjoyed this lesson. Join me next time for a lesson called Using Functions. Bye-bye for now.